Hello everyone, welcome back. This is Kasi Lakshmanan. This is a continuation of the short video which is part of the E104 Advanced Deep Learning class. The topic for today is neural networks for disease detection. In recent years, AI assist features have been potentially very helpful to medical professionals and may get millions of people access to the healthcare that they otherwise would not have access to. For this particular exploration, we will be building three class of models, a baseline model, a champion model, and a challenger model. For the baseline model, we will be considering a CNN model, a champion model, which will be a fully and partially fine-tuned ConVNeXt model, and two challenger models, one with the EfficientNet and another with the shifting window transformer. These models are basically computer vision image classification models for disease detection problems. As we considered the methods for solving this potential problem, we looked at this website that has accumulated recent ML contests and the state of competitive machine learning. This is a website that basically recently published, which summarizes about 300 plus competitions from not only Kaggle but a few others, and does a deep dive about 60 plus winning solutions. From this website, we specifically looked at computer vision, and when we looked at computer vision for 2013, CNN topped the list of the most winning architectures, followed by transformer and a combination of CNN and transformer. In specific, when we looked at methods, ConVNeXt topped the list of most of the winning competitions, followed by UNet, SWIN transformer, EfficientNet. Of these, we selected ConVNeXt, SWIN transformer, and EfficientNet for our exploration. This is a very helpful website above and beyond the computer vision methods. It also summarizes a lot of the other winning solutions for other domains of area. So I really recommend you to check this out. Okay, let's get back to solving our problems. The dataset that was used for this exploration is an Alzheimer's dataset from Kaggle. The data is sourced from OASIS, which is an open access series of image studies. There are about 4,000 training images and about 1,000 test images in this dataset. After some initial data exploration, we can look at the images. The image size is about 208 by 176 3 channels. And what we see, we do the initial steps of splitting training, validation, and test. And we look at the distribution of the target class. In this case, let's look at the distribution of target class by the training, validation, and test counts. We can notice that the moderately demented class of the four classes is very underrepresented. You can also look at a quick visualization of all of the four um, test labels and understand the corresponding images just to see how they look like. Next, we do some initial data treatment, but let's go into the section where we start to build the analytical models. Convolutional neural network was the one that was first used as a baseline model. For this model, we defined some callbacks, early stopping callback and the model checkpoint callback to look at the validation AUC and save the best model. We also defined the exponential decay metrics here. Nothing special, usual convolutional layers. Let's move on to the champion model. The champion model was built using the PyTorch architecture. First, let's define the data transformations. In this case, the images were resized to a 224 by 224, and some data augmentation steps were done, and then the normalization was done across the training, validation, and test images. Then next step, we load the datasets for the corresponding test, validation, and train dataset, and we do the data transformations as well. These datasets are then eventually loaded into the data loader with a batch size of 4. Next, before we start building the model, we will define a function for the training epochs, which will take a model, data loader, the loss criteria, the optimization. Nothing interesting here. The validation specifically is in the evaluation mode. Next, we define the train model function, which basically inside a context manager um, saves the best model within each epoch and then compares the model with the previous best model and then saves if it has a better validation accuracy. Now that we've defined the functions, we are ready to go and build our second set of champion models. In this case, we will first build the fully fine-tuned model. For this fully fine-tuned model, we will be using the ConVNeXt base model with the image 1000 ImageNet 1000 version 1 weights. We define those weights. We will be using a loss criteria of a cross entropy loss, and an optimizer is going to be the stochastic gradient descent. We also dabbled with the Adam optimizer, but it did not produce any better results than the stochastic gradient descent. We also defined a exponential loss scheduler, and then we are off to go train this model for 100 epochs. The best model produced a validation AUC of a 0.7083. Now let's look at the partially fine-tuned model. In this case, only the final layer or the head layer of the model was trained while freezing the rest of the network. For this, the same all else constant was used. The ImageNet 1K version 1 was used here, cross entropy loss as a loss criteria, and the stochastic gradient descent and exponential learning rate. The best model only had a validation accuracy of a 0.5668. What we will do next is go ahead and evaluate these two models on the test set. When we evaluated the model on the test set, we found that the area under the curve ROC on the test dataset was a 0.689. This was the fully fine-tuned model, and for the partially fine-tuned model, we had a AUROC of a 0.559 on the test dataset. In addition to AUROC, we also looked at other metrics like precision, recall, F1 score, and support. And we will make those model comparisons later. Now let's look at the challenger model. For the challenger model, we built two models, an EfficientNet model and a shifting window transformer. For the EfficientNet model, we first start off with test validation and train split. And then we define the early stopping callback with 10 patients. and then the model checkpointing for the best validation AUC model, and then the exponential decay criteria. In this case, we included the top, and the weights were random initialized for the flow 4 classes. And we trained this model for 100 epochs. At this stage, we can see that the ROC AUC was a 0.99 on the validation data. We will now evaluate this model on the test dataset. On the test dataset, we had a AUROC of a 0.8980, which is by far the best model that we've seen so far. Next, we will build a second flavor of the same EfficientNet model. But in this case, what we will do is we will not include the top layer, and then the top layer is built with average pooling and batch normalization and dropout. All other considerations were placed exactly the same. The callbacks, the metrics, and exponential decay were exactly the same as before. We trained the model for 100 epochs, and the validation AUC reaches about a 0.8853. Now what we will do next is evaluate this model on the test dataset. When we evaluated the model on the test dataset, we have about 0.8459 as the test AUC, which is not bad compared to the other models we've seen before. Finally, the last model we'll see today is the shifting window transformer. For this model, we will be using 8 attention heads with embedded dimensions of a 128, which is slightly different from the 64 default. The input data shape will be 224 by 224 by 3 for the 4 classes. We'll go ahead and train the model. This model produces a validation ROC of about a 0.8937. What we will do next is evaluate this model on the test dataset. On the test dataset, we have a test AUC of a 0.75. Before we move on and compare all of these models, let's look at this, the model prediction visualizations. One of the important features that we need to explore is to be able to provide doctors and radiologists with a feature where we can provide another layer of predictions, where we can take the deep learning model predictions from the penultimate layer and cast them into prediction heat maps. An example is shown below here. Let's look at some test cases. The first one is a very mild demented case in which this is the original image, and this image shows a lot of yellow highlights of the heat map, which correspond with a very mild demented designation on the test labels. Now let's look at a case for non-demented. You can see here clearly that there are not many highlighted yellow regions. So this produces some level of alignment with the ground truth. So now let's look at the conclusions that we can arrive at from model comparisons. Overall, what we see is that the champion model with pre-trained weights from EfficientNet B0 produces the optimal results. Of all of the 7 models, in general, only the maximum disease detection rate is about 42%, which is a very low detection rate and may not be very meaningful for a problem of this importance. So there should be more work that's done. And this could be a direct correlation of the low number of test and validation images, as well as the effectiveness of the data augmentation steps. Another thing that could contribute to this is the very low event rates for some of the target classes. Some of the models that did not show much promise that we expected is the sliding window transformer and the champion partially tuned ConVNeXt model. And finally, the base CNN model with data augmentation. Some of the models we thought did fairly well is the pre-trained model from scratch from the EfficientNet B0 and the fine-tuned version of the same EfficientNet B0. In particular, the Challenger model uh, pre-trained from scratch, the EfficientNet B0, actually produced generalized very well with a ROC of a 0.89 on the test data. This had about 41% detection rate and 61% of the uh, false discovery rate. So based on this, we could conclude that this is the best model um, from the models that we built today. The table below shows a comparison of all of this test AUC, validation AUC, and the decrease in the validation AUC, as well as some of the precision recall metrics as well. So let me conclude by saying thank you for watching this video and see you soon.